So we'll do some more examples with related rates. Remember, tomorrow is your test on derivatives and applications of derivatives. You are not given any of the derivative rules, so you'll have to know those. And you also receive the review assignment that you should have done for tomorrow. It is one of the best things you can do to prepare for that test. If you can do everything on the review assignment, you'll be fine for the test tomorrow. So make sure you get that done. And it needs to be handed in for marks. All right, related rates, part 2. A spherical balloon snowball is melting in such a way that its volume is decreasing at a rate of 1 centimeter cubed per minute. Determine the rate at which the radius is decreasing at the moment when the radius is 5 centimeters. So again, with these related rate problems, you're going to be given the rate of change of one aspect with respect to time, and you're going to be asked to find the rate of change of another aspect with respect to time. Always a good idea to list out what you're given and what you're trying to find. So you're told the volume is decreasing, so that'll be the rate of change of volume, dV by dt. And because it's decreasing, it'll be negative 1 centimeter cubed per minute. You want to know the rate at which the radius is decreasing, so dr by dt is what we're looking for at the moment when r is 5 centimeters. So that is what we're given and what we're trying to find. So we need to have a formula, a relationship between volume of a sphere and its radius. And the formula for volume of a sphere is a function of r, the radius. It's 4/3 pi r cubed. And again, you'll be given any of these formulas that you need for the test tomorrow, whether it's volume of something or area of something, you'll be given those formulas in the question if you need it. All right, so in this case, there's only one variable, r. We saw examples yesterday where sometimes there was two variables, and so we need to do some work to express one variable in terms of the other. But in this case, there's only one variable, so we can differentiate both sides with respect to time. So derivative volume with respect to time is dv by dt. When you differentiate the right side, again, you have to use the chain rule, which has two parts. The first part of that is the power rule. So the exponent 3 comes in front. It'll actually cancel with the 3 on the bottom, so just with 4 pi r squared. And the second part is taking the derivative of what's inside the bracket. The derivative of r with respect to time is dr by dt. We need that in our equation because that's what we're trying to find, dr by dt. So now we can find out what dr by dt is when dv by dt is negative 1 centimeter cubed per minute. That equals 4 times pi times the radius, which is 5 centimeters squared, times dr by dt. So we can do some simplifying on the right. 5 squared is 25 times 4 is 100. So that'll be 100 pi centimeters squared dr by dt. You also squared the centimeters, so that's where the centimeter squared comes from. And then to get dr by dt by itself, we would divide both sides by 100 pi centimeters squared. And then we can say that dr by dt will equal negative 1 over 100 pi. So we divided centimeters cubed by centimeters squared, which gives us centimeters per minute. So that is the rate of change of the radius with respect to time. Negative 1 over 100 pi. And as we did yesterday, we're keeping these as exact values. If you're asked to round to a certain decimal, then you can do that. But otherwise, we'll keep them as exact values. So number 2, a conical glass vase is being filled with a liquid at a rate of 10 centimeters cubed per second. So the fact that it's centimeters cubed tells us its volume. Right? Tells us its volume. And if you think about it, I mean, as the glass is being filled, the volume is going to increase. So that is the rate of change of volume with respect to time, 10 centimeters cubed per second. So the vase is 20 centimeters high with a radius of 3 centimeters at the top. Determine the rate at which the height of the water is rising. So we want to know what dH by dt is at the moment when the height h is 10 centimeters. So that is what we're given and what we're trying to find. So we need to have an expression, an equation that relates volume of a cone to its height. And the formula for volume of a cone is volume equals 1/3 pi r squared h. So there are two variables here, the variable r and the variable h, and they both will change. Right? As water is being added to this vase, the radius at the top of the water is going to change as well as the height. But if you look at what we're given and what we're trying to find, we're given dV by dt, we want to find dH by dt. We are not told anything about the radius. We're not asked to find what the rate of change of radius is. So if we were to differentiate this equation as it stands right now, we would have to use the product rule, because the pi r squared would be the first factor, h would be the second factor. You'd have to use the product rule to differentiate that, and you'd also have r and dr by dt in there, which we can't have because we're not given any information about dr by dt. We're not asked to find it. So we need to do something to eliminate that variable r from our equation. And so we can do that, and we saw one like this yesterday. The ratio of the radius to the height will be 3 to 20. Because at the top, the radius is 3 and the height is 20. So the ratio of radius to height will be 3 to 20. And that ratio will stay constant no matter where you are. Yes. What? But you still would have r in the equation. You probably could, but then I think that it'd be much more complicated because you'd have to take the square root, right? So it would make it much more complicated, but it could work. So we want to find what's happening at the moment when the height is 10 centimeters. So we want to know an expression for r. Well, I guess, let me back up here. I can get what r is in terms of h just by cross multiplying now. So when you cross multiply, it'll be 20r equaling 3h. So r will equal 3h over 20. So that's what we'll sub in for r in the equation. So now we will say that v equals 1/3 pi times the radius, which is 3h over 20 squared, times h. So this will be 1/3 pi. So when you square the 3h, you'll get 9h squared over 20 squared is 400 times h, which will simplify this. The 3 goes into the 9 3 times. So on top, we're going to have 3 pi over 400 h cubed. So we can write that like I've done here with a coefficient of 3 pi over 400 h cubed. So that's what volume is. And now we'll differentiate both sides with respect to time. So dV by dt will equal, on the right side when we differentiate, again we use the chain rule, which has 2 steps. The first step is using the power rule, so the exponent 3 is multiplied by what's in front. And so it'll be 3 times 3 pi, which is 9 pi over 400 h squared. And the second part is of the chain rule is multiply by the derivative of what's inside the brackets, which would be the derivative of h, dh by dt. Okay, so we're given dv by dt. That is 10 centimeters cubed per second. And that equals 9 pi over 400 times h, which is 10 squared, 10 centimeters squared, times dh by dt, which is what we're trying to find. What is dh by dt? The rate of change of height with respect to time. So on the right side, 10 squared is 100, and that 100 on top will cancel with the 400 in the bottom, which will just leave us with 9 pi over 4 centimeters squared dh by dt. And now we will divide both sides by the 9 pi over 4 centimeters squared. So that'll give us dh by dt by itself. And when you divide by a fraction, 9 pi on 4, it's the same as multiplying by the reciprocal. So we can multiply by 4 and divide by 9 pi. So when the 10 is multiplied by 4, it'll be 40 over 9 pi. And you're dividing centimeters cubed by centimeters squared, which leaves us with centimeters per second. So 40 over 9 pi centimeters per second is the exact rate of change of height with respect to time. Okay? This next question is exactly the same. Exactly the same. We're given the volume of a cone, and you want to find the rate of change of height with respect to time when the height is 2 meters. So exactly the same. I'm not going to do that one, but let's look at number 4. A spotlight sits on the ground and shines on a wall that is 10 meters away. A 2-meter tall man walks away from the spotlight and towards the wall at a rate of 1.2 meters per second. How fast is the height of the shadow on the wall decreasing at the moment when he is 3 meters from the wall? So we can form a right triangle for this. So the height of the right triangle represents the wall. So we've got a spotlight on the ground and shines on the wall that is 10 meters away. The man is 2 meters high. So there's our man, and he is 2 meters high. He walks from the spotlight toward the wall at a speed of 1.2 meters per second. So if we say that the base of this triangle is x, the rate of change of x with respect to time is dx by dt, and that is 1.2 meters per second. So as he walks towards the wall, the shadow on the wall is decreasing. The height of it is decreasing. And we want to find how fast the shadow on the wall is decreasing. So if we say that that is h, we want to find dh by dt. At the moment when he is 3 meters away from the wall, which means he has traveled 7 meters, okay, or he is 7 meters away from the spotlight. So at the moment when x is 7. When he is 3 meters away from the wall, which means he is 7 meters away from the spotlight. And it's the spotlight that is determining the shadow. So that's why we have to use that number. Okay, so this one's a little bit different than the ones we looked at yesterday, because the ones we looked at yesterday involving a right triangle, we use the hypotenuse. In this case, we're not going to use the hypotenuse. We don't know anything about it. We're not asked to find anything about it either. So we need to come up with a relationship that just involves basically h and x, okay, is what we have to do. All right, so here's what we can do. We can write a relationship here, and that is that if we take h, which is the height of the wall, over 10, which is the entire base of the right triangle, because the spotlight is 10 meters away from the wall. So the ratio of y, or I'll say h, not y, h over 10 must equal 2 over x. So what we're doing here is we're using similar triangles. The first triangle is the large triangle. The second triangle will be the one from S to the man, which is 2 meters tall. That's where the 2 comes from. So they're similar triangles. They're similar triangles because the angles will be the same. They're both right triangles. They share the angle at S. Right? So if 2 angles are the same, the third angles must also be the same. The angles at the top of each triangle will be the same. So they are similar triangles. And with similar triangles, the ratios of the sides will always be the same. So we did the ratio of the height over the base of the large triangle, h over 10, must equal the ratio of the height and base of the second triangle, which would be 2 over x. And again, x refers to how far you are away from the spotlight. So if you cross multiply here, you'll get h times x equals 20. And then h will equal 20 over x, or h equals 20x to the negative 1. So there is an expression that we can use. Right? Our equation must have x in it because we're given dx by dt. It also must have h in it because we want to find dh by dt. We have that. We have an expression that relates those two variables together. So now we will differentiate both sides with respect to time. So you'll get dh by dt equals, when you differentiate the right side, again, there's 2 steps. You must use a chain rule. The first step is the power rule, so the negative 1's multiplied by the 20 in front. The power decreases by 1, and we also multiply by the derivative of x with respect to time, dx by dt. So dh by dt will equal negative 20 over x squared dx by dt. We want to find dh by dt here. X is 7, so it'll be negative 20 over 7 squared times dx by dt, which is 1.2 meters per second. So it'll be negative 20 times 1.2, which is what, negative 24, I think, times 1.2, whoops, 0.2, yeah, negative 24 over 49 meters per second. So that's the rate of change of the height with respect to time. So this is something that's brand new. We haven't done one like this before. On the test tomorrow, you won't get any of these that you haven't seen before. Okay, because that's difficult to know how you would relate, how you'd get the equation to start with in order to differentiate. So anything you see on the test tomorrow, you will have seen before. Okay? So you won't be expected to try and figure out what the relationship is that you need to differentiate. Number 5, we saw one like this yesterday. A man starts walking north at a rate of 1.5 meters per second. A woman starts at the same point and time walking west at a rate of 2 meters per second. Who's right? Who's right? No, definitely not. Definitely not. Who's right? Well, obviously the man, right? Ladies, you would agree with that? No. Okay, so man walks north, so we got the man walking north, and then the woman's walking west. So we saw one like this yesterday with 2 ships that passed the buoy, right? So this will be done the same way. So the man is walking north, so if we say that variable is y and the woman is walking west, so we'll say that variable is x. So if the man is walking north at 1.5 meters per second, that'll be the rate of change of y with respect to time. So that'll be dy by dt. dy by dt is 1.5 meters per second. And then you have the woman that's walking west at a rate of 2 meters per second. So the man is walking slower because he knows that the woman is eventually going to realize that she did wrong and she's going to turn around and come back and say sorry. So that's why he's going slower, because he knows this is going to happen. Right, Chance? No. Okay. Determine the rate at which the distance between the two is increasing 1 minute later. So the distance between the two will be represented by the hypotenuse. So if we give that a variable, let's say z, we want to know what dz by dt is. So we're given dy by dt, we're given dx by dt, we want to find dz by dt. So we have to keep all 3 variables in our relationship. We need to relate all 3 together, which we can do again using Pythagorean theorem. So x squared plus y squared equals z squared. And now we're going to differentiate everything with respect to time. So it'll be 2x dx by dt plus 2y dy by dt equals 2z dz by dt. So we also need x, y, and z, which we can find. We want to find the rate that the distance between the two is increasing 1 minute later. So if the man walks at 1.5 meters per second, you'd have to multiply that 1.5 by 60 to get how far he's traveled in 1 minute. Right? We're given his rate in meters per second. There's 60 seconds in a minute. So in this case here, y would be found by going 1.5 times 60, which is 90 meters. X will be found by going 2 meters per second times 60. That'll be 120 meters. And once we have those, we will find z by again using Pythagorean theorem. Z squared will be 90 squared plus 120 squared. So if we go to our calculator to do that, 90 squared plus 120 squared. So z squared will be 22,500. And z will equal the root of that. And Brighton, the human calculator, knew that already, didn't even need to use a calculator. 150. So we need x, y, and z because when we differentiate, there's factors of x, y, and z in there. So we need those. So we want to find out what dz by dt is. So I've got 2 times x, which is 120 meters, times dx by dt, which is 2 meters per second, plus 2 times y, which is 90 meters, times dy by dt, which is 1.5 meters per second, and that equals 2 times z. Z was 150 meters, times dz by dt. So on the left side, 2 times 120 is 240, times another 2 is 480, and that would be meters squared per second, plus 2 times 90 is 180, times 1.5, I think is 270 meters squared per second, and 2 times 150 on the right is 300 meters, dz by dt. 480 plus 270 is 750 meters squared per second, equals 300 meters dz by dt. And then we would divide both sides by 300 meters. So dz by dt will equal 750 divided by 300 is 2.5. And you divided meters squares by meters, which gives us meters per second. So that's the rate of change. The rate of change that the distance between the two is increasing. Well, there might be. You've seen a couple like this, right? Did one yesterday and one today. Yes. Oh, yeah. You will get a formula sheet. Yep. You don't get one tomorrow for the test. You have to know those differentiation rules. But after that, you'll be able to allow to use formula sheets. Okay, so the area of a triangle is increasing at a rate of 79 centimeters squared per minute. So we did one yesterday where it was an equilateral triangle. This one isn't an equilateral triangle. Okay, it can be a little bit different. The area of a triangle is increasing, so that'll be dA by dt. Increasing, so it's positive 79 centimeters squared per minute. Right. Also, the fact that it's centimeters squared per minute tells us that it's area. We've seen a couple today where it was volume, and that was units cubed per minute or per second. So its height is increasing at a rate of 2 centimeters per minute. So that'll be dH by dt. 2 centimeters per minute. Determine the rate at which the base of the triangle is increasing. So that might be dB by dt. At the moment when B, the base is 30 and the area is 105. So the base is 30 centimeters and area is 150 centimeters squared. So that's what we're given and what we're trying to find. So the area of a triangle is 1/2 base times height. That's the formula for area of a triangle. And in this case, we need to keep both of those variables here. Yes. Oh, thank you. That will make a difference. So we need both of those variables to be kept in this equation because we're given dH by dt and we want to find dB by dt. So we need to keep both of those variables in there. So when we differentiate now, we will have to use the product law, because on the right, it's a product. The first factor is 1/2 b, the second factor is h. We have to use the product law. So the derivative of the first factor, the derivative of 1/2 b to the 1 will just be 1/2 b to the 0 if we want. So that's the derivative of the first factor times the second factor, which is just h, plus the derivative of the second factor would be 1h to the power 0 times the first factor, which is 1/2 b. Oh, and I forgot, excuse me, to put the second part, which is the chain rule. I have to have the dB by dt in the first one and the dH by dt in the second. So let me fix that. So we'll have dB by dt, and we'll have dH by dt. So we can take the b to the 0 and the h to 0, and I just wrote them in there because technically that is what's happening. So it's going to be h over 2 dB by dt plus b over 2 dH by dt. So if we look at this, we need h, which we don't have. However, we do have the fact that the base is 30 and the area is 105, so we can use those two along with the area formula for a triangle to find out what h is at that point. So we're going to have to do that before we can get our answer. So let's do that. Again, the area of a triangle is 1/2 base times the height. We're given the area to be 105 centimeters squared. We're given the base to be 30 centimeters. We want to find h, the height. So 1/2 of 30 is 15. So that'll be 15 centimeters times h, the height. And if you divide both sides by 15 centimeters, we'll have h, the height. And 105 divided by 15 is 7, and centimeters squared divided by centimeters is centimeters. So now we have everything that we need. So again, I've got dA by dt if I write out the formula again, is h over 2 dB by dt plus b over 2 dH by dt dA by dt is given to be 79 centimeters squared per minute. And that will equal h, which is 7 centimeters over 2 times dB by dt, which is what we're trying to find, plus h, which is, sorry, that's b. b is 30 over 2, 30 centimeters over 2 times dH by dt, which is 2 centimeters per second, or per minute. I'm kind of run out of room here, so I won't put the units for that. But I've got 79 centimeters squared per minute equals 3.5, or 7 over 2 dB by dt. I guess what I could have done here, I could have just subtracted the 30 from both sides because what happens is the 2's cancel. But anyways, so that'll be 30 centimeters squared per minute. And now I'll subtract that 30 from both sides, which will give us 49 centimeters squared per minute equals 7 over 2 dB by dt. And so we'll divide both sides by the 7 over 2, which is 3.5 centimeters. And so on the left side, when you divide 49 by 3.5, you actually get 14. Centimeters squared is divided by centimeters, which gives us centimeters per minute. So there's dB by dt. So again, when you're setting up your original relationship, the formula, you need to look and see what you're given and what you're trying to find, and that'll tell you if you have to use the entire formula like this one, or if you have to do some substitution to eliminate one of the variables. And we've seen a couple examples like that. So you should work on page 145 to 146, questions 1 through 9, 11 and 12 for practice. I will post the solutions on Google Classroom so you can check your work. Remember, you want to get that review assignment done before the test tomorrow. It's the best thing you can do to help you get ready. You'll be given every formula that you need on the exam, right? But you need to know what those differentiation rules are. So spend some time maybe looking over the quiz that we went through, that derivatives quiz. Spend some time going through that, as well as what we've learned this chapter about applications of derivatives, right? Remember, we took the derivative position function to get velocity, the derivative velocity function to get acceleration. So that's part of this, right? As well as these related rates. Okay?